to your first-hand view of a flipped classroom. What I plan on doing today is, I guess, presenting today's material over video to you in hopes that if you really want and don't understand something, you can go back and view this over and over. This is my first experience with a flipped classroom, possibly something that I might try and do more and more with you, and then of course being able to embed it into Edmodo. Today's discussion, what we're going to be looking at is we're going to be talking about specific heat. I guess to start talking about specific heat, one of the questions that I want to pose to you is, I want you to think of a nice cool July day. We'll say it's 80 degrees out, and you go down to the local pool and you're willing to go to that diving board and dive right on in. But let's say that it's an 80-degree day in March and you go to the river. Why aren't you willing to jump into that river? Okay? Or, let's look at it this way. Again, a nice warm July day. This time we're going to go to an extreme and we're going to say it's 100 degrees out. You're walking across that cement and it's extremely hot. But yet you dive into that water and that water's cool. Well, what it has to do with is it has to do with the chemical makeup of each material. Not all materials are the same. Yesterday when we talked about conductors and insulators, we said some materials are going to move electricity or energy easily. Things like glass, wood, rubber, plastic, those are going to be insulators. Their chemical makeup didn't allow energy to flow easily. Specific heat is one of those things that, again, some things are going to heat up quickly, other things aren't going to heat up so quickly. Specific heat is really just going to be the energy that is needed to raise a 1 kilogram substance by 1 Kelvin temperature. Again, going back to what I set up at the beginning. On an 80-degree summer day, you're willing to go down to that swimming pool because it's had May, it's had June, had those days in July to warm up. That water is going to hold its temperature for quite a while. But yet if we go to an 80-degree day in March, you know that that river is going to be cold. And that river is going to be cold because it hasn't had the hot sunny days to warm that water up. Going to that hot day in July, the cement's extremely hot. It's hot on your feet. Because again, cement has the makeup that when heat hits it, it absorbs it quickly and it gets hot. Water, on the other hand, it takes a long time to heat up. And as it takes a long time to heat up, you dive off that diving board in a 100-degree day, and the water feels nice and cool to you. When you look on page 444 in your book, page 444 has a bunch of specific heats that you need to pay attention to. The one that I want you to notice is the specific heat for water. And the specific heat for water is 4,180. The units on that, joules per kilogram Kelvin. And when you compare that number to every other number on that chart, you're going to notice that water is the highest, meaning it takes the most energy to heat a 1 kilogram substance up. Again, when you look in your book, aluminum's at the top of the chart. Aluminum needs 900 joules of energy to raise it by 1 Kelvin temperature. It basically takes 4 times as much energy to raise 1 kilogram of water up that same 1 degree. You go to something like copper. Copper's only 385. again, you're basically talking about something that's a little over, what, 10 times as much? So again, water takes a long time to heat up. But also, once water has that energy, it's going to take water a long time to cool down. If any of you have ever been to California, California's climate is usually off by about, 2.5 months. Took a honeymoon there. In December, me and my wife went out to California, and we're walking along the bay, the San Francisco Bay, and there's people out there swimming in the middle of December. The middle of December, they are swimming. Well, here's the reason why. Again, San Francisco sits on a large body of water. As that sun shines down, it takes a long time for that water to heat up. But once that water has heated up from all of the summer high temperatures, in December that water is still going to be warm and you're still going to see people swimming. If any of you have ever watched a San Francisco Giants baseball game, baseball starts in April. A lot of people, you'll see them in jackets and things like that. And again, the reason why you see them in jackets is finally that temperature of that water has cooled down. And as the winds are blowing off of the bay, it's blowing those cooler temperatures into San Francisco. So again, an April day in Nebraska might be nice and warm, but an April day in San Francisco is going to actually be cool because again, the city of San Francisco is on that San Francisco Bay, and being on that San Francisco Bay, again, it's going to take that water a long time to heat up, so therefore it's blowing those colder temperatures in. What I want to do is I want to focus on really how to calculate specific heat. To calculate specific heat, the equation is going to be E is going to be equal to M delta T Cp. Okay? E is going to stand for energy. M is going to stand for mass. Delta T is going to be your change in temperature. And Cp is actually going to stand for your specific heat. Now if we go ahead and focus on the units, okay? E is going to be measured in joules. Joules is going to be your standard unit for energy. Now the thing that I want to tell you is this. If energy is being gained, you're going to have a positive energy or a positive joules. If energy is being lost, energy is going to be negative. Mass, just like your SI base unit, it's going to be measured in kilograms. Now, I guess I should come back up here to joules. Basically, to shorten it up, we're going to have J standing for joules. Change in temperature. Change in temperature is going to be measured in Kelvin. Because if you think back, and I know I kind of, it's up here. Let me go ahead and slide up just a little bit. Joules, kilogram, Kelvin. Okay, it's going to be in this SI base unit of Kelvin. And then specific heat, the units there are joules per kilogram Kelvin. Now, one specifically that I want to look at is I want to focus right here on change in temperature. Change in temperature means that we must be doing a difference here. We're doing a difference between your ending temperature and your beginning temperature. So change in temperature is going to be equal to, you're going to take your final temperature, and that's going to be TF. TF is going to stand for final temperature. And you're going to subtract off your initial temperature. I, initial temperature. Initial also means your beginning temperature. If you want to think of it this way, think of it as final temperature minus your beginning temperature. So really when you do this, you have to do this portion of the equation first. Okay? Anytime you have two temperatures, we're going to have to do what we have in parentheses first. Now, like I said, water's specific heat, that's one that I'm going to want you to know, or that's one I'm going to want you to memorize. Okay? Any other one, either in a quiz problem or if it's homework, you can use your book, or I'll put the table on the quiz or the homework. Or actually in the statement itself, I might say the specific heat of silver is this. Well, what I want to do is, I want to go ahead and look at a couple of sample problems. And those sample problems that I want to look at are right here. The first one says, how much energy is needed to raise the temperature of 5.78 kilograms of sand from 32 degrees Celsius to 54 degrees Celsius? So I'm going to go up, okay? Here's the thing. The question says, how much energy? Now, I guess one thing that I should probably put up, which I maybe should have done back on the previous page, and we'll go ahead and open that page back up, okay, is I need to go ahead and give you the circle equation, okay? Now, this is going to be a modified circle equation, but can still be used exactly the same way. The circle equation, we'll actually go ahead and make an oval here. Okay? On top is going to be your energy. Okay? So energy is the one that you have to remember is on top. On the bottom is going to be your mass. On the bottom will also be your change in temperature. That's a terrible triangle. There we go. That's a little better. And on the bottom we're also going to put CP. Now there might be times where I tell you that there is an unknown sample. Okay? And if there is an unknown sample, you're going to have to solve for the specific heat. So let's go ahead and let's get back to our sample problems. Getting back to our sample problem, again, it says here, how much energy is needed? So I'm going to go ahead and solve for my energy. Okay. Solving for my energy here, I'm going to say that energy is equal to, okay, the mass, okay, that's right here, M, 5.78 kilograms. So I'm going to go ahead and plug that in, 5.78 kilograms. Now, if you remember what I said, change in temperature. Change in temperature was equal to TF minus TI. Now here's the thing. It says 54 degrees Celsius. If you remember what I said we have to convert this to Kelvin. So let me grab a calculator real quick. Grabbing my calculator, I'm going to take 54 and I'm going to add 273. Because remember what we said. Kelvin is equal to Celsius plus 273. So when I take 54, because this is what it ended at right here. Okay? There's my TF. 54 plus 273 is going to be equal to 327. Minus, okay, right here. There's my initial temperature. That's my beginning temperature. But again, I have to convert that to Kelvin. So I'm going to take 32 plus 273, and I'm going to get 305. And again, both of these are in the units of Kelvin. Now, the last important piece of information is I need the specific heat. When I read through this, it says how much energy is needed to raise the temperature of 5.78 kilograms of sand. So, I'm going to go ahead and go to my book. And sand is all, let's see, 3 up from the bottom. And it says here that it has a specific heat of 670. So 600. Okay, let me get my pen working. Not sure why. There we go. 670 joules per kilogram Kelvin. Well, again, working it through. Okay, 5.78 kilograms. Okay, 327 minus 305, well, that's going to be 22. So we've got 22 Kelvin multiplied by 670 joules kilogram Kelvin. Now let's go ahead and look here. I've got a kilogram on top, I've got a kilogram on the bottom. Those units will cancel. I've also have a Kelvin here and a Kelvin here. So those units will cancel. And the thing is, the only unit I'm going to have left is going to be a joule. Okay? So I'm going to go ahead and plug in 5.78 times 22 times 670. And when I run that through, I find out that my energy is equal to 85,197.2 joules. I want you to notice, I have a positive energy. Look what happened to my temperature. We went from 32 to 54. And if you get hotter, it is going to be positive energy. Okay? It's going to be positive energy. So again, this is solving for energy. Well, let's look for one if we're not solving for energy. And I guess one thing too, if you want to go ahead and look at that circle equation, again, we were solving for energy. You would have put your 5.78 down there. Okay? Now, if we actually do this subtraction, 327 minus 305, we would have put our 22 there. And then our specific heat, 670. And again, you can see we're just multiplying straight across, and when you multiply straight across again, you still get that 85,197. Well, let me go ahead and look at our last sample problem. Our last sample problem right here. It says we have a sample of copper. Okay? That's going to be important. It says it goes from 30 to 25. Notice, 30 to 25. We're cooling down. And if you cool down, it means we're going to lose energy. It says 253,124 joules of energy is lost. Notice what it says there. It says energy is lost. Anytime energy is lost, it really means that we have a negative 253,124 joules. Lost energy is going to be negative. Now the question says, what is the mass? Okay? What is the mass? So I'm going to go ahead and look at my equation. Energy is going to be equal to M delta T CP. Okay? Now, if you don't like seeing that delta T, because I know we are going to have to do something with it, maybe you want to look at it like this. Okay? Knowing that we have to do something different with it, maybe you want to put up there already TF minus TI. That's up to you. You decide. Or you could really do it over here and then plug it in to the equation. But energy, negative, because energy was lost. We're going to put in negative 253,124 joules is going to be equal to. Now the question says, what is the mass? Anytime you see that what means a question. So I'm just going to go ahead and put my M in there. Okay, final temperature. We ended up at 25. Okay, so again, I'm going to get my calculator out. I'm going to take 25 and add it to 273, and I get 298. Minus. Starting out temperature. Starting temperature was 30. 30 plus 273. Probably a lot of you did that in your head faster than I had it on my calculator, but you'll end up with 303 Kelvin. Only other piece of information I'm missing is my specific heat. What is the substance? The substance is copper. Again, I go back to my table. That table's on page 444. I find copper, it's the third one down, and it says there copper has a specific heat of 385. 385 joules, kilogram, Kelvin. Okay? Now, if we go ahead and do this portion right here, 298 minus 303, we end up with a negative 5 Kelvin. Now, if you want, you can go ahead and do the algebra behind this, but what I'm going to do is I'm going to actually look at our circle equation. Okay? Looking at our circle equation, go ahead and make it nice and big here. Remember, energy goes on top, so let's go ahead. Let's first draw it up. M delta T Cp. Okay, here's the energy. So I'm going to go ahead and erase and put them in. Energy, gone. So let's put that number in. Negative 253,124. Okay, M, I don't know what that one is. Okay, change in temperature. This one right here. We did the subtraction, and when we did the subtraction, we got a negative 5. So let's get rid of that one. Let's plug in that negative 5. Okay, negative 5 Kelvin. This one was joules, okay, because you know that I always like to see the units on that. Cp. Okay, again, we said it was copper. We looked that one up on page 444, and we said copper had a specific heat of 385. Let's go ahead and get rid of that one. 385 joules, kilogram, Kelvin. Now, remember what you do. Cover up the M. Okay, that's the one we're trying to solve for. You're going to take this number here and divide it by negative 5. You're going to take this number here and divide it by 385. And when I do that, okay, so negative 253,124. And I'm going to divide it by negative 5. And I'm going to divide it by 385. And my calculator is going to give me an answer For some reason my pen doesn't want to work. Let's try this one over here. There we go. Okay. Alright. Calculator spits out an answer of 131.49. Notice, joules, joules. Okay, joule on top, joule on the bottom, those will cancel out. I've got a Kelvin, and I've got a Kelvin. The only unit that's going to be left is kilograms. And kilograms is a measure of mass. I really hope you've enjoyed this version of specific heat as the flipped classroom. Your assignment, okay? Your assignment is going to be, let me scoot this on down, is going to be to read pages 444 to 445. I want you to do questions 3 through 5 that are on page 445. And I also have a worksheet over specific heat. Thank you, and have a good day.